Hello everyone, we're continuing our discussion of canonical correlation analysis, and today the lecture is going to be on large sample inference. So how can we do hypothesis testing in the context of canonical correlation analysis? So let's start with a discussion of test of independence between y and x. So recall that what we discussed at the beginning is that CCA is trying to explain the covariance matrix between y and x. And so if there is no correlation between y and x, the covariance matrix is simply zero. And in particular, any quadratic form of the form A transpose times the covariance matrix times B is going to be equal to zero as well for any choice of A and B, and therefore all of the canonical correlations are equal to zero. So to test for independence between y and x, we can use a likelihood ratio test, as we discussed during the lectures on tests for covariance matrices. So here's the setup. Let yi xi be a random sample from a normal distribution of dimension p plus q, where the covariance matrix sigma can be decomposed as such in a block fashion. Let sy and sx be the sample covariances of y1 to yn and x1 to xn respectively. And let Sn be the p plus q dimensional sample covariance matrix for the pairs yi xi. Then the likelihood ratio test for H0 being for the null hypothesis being that the covariance matrix is equal to 0, will reject the null hypothesis for large values of -2 times the log of lambda, just as usual. And as we saw in our discussion on tests for covariance matrices, this is equal to n times the log of the ratio of the determinant of Si times the determinant of Sx over the determinant of Sn. Now, what is different is that in the context of CCA, we can rewrite this using the canonical correlations. And so this test statistic now can be written as -n times the log of the product of 1 minus the canonical correlations squared. Where, of course, rho hat 1 to rho hat p are the sample canonical correlations. So we'll prove the second inequality. Of course, the first one just follows from the discussion from a previous lecture. So first note that the equality we want to prove is equivalent to showing that, essentially on the original scale, that we have lambda to the power 2 over n, which is equal to the ratio of the determinant of Sn over the product of the determinant of Sy and the determinant of Sx. We want to show that this is equal to the product of 1 minus rho hat I squared. And so we're going to prove this using the formula for the determinant of block matrices. So first we can decompose Sn into a block matrix where we have Sy, Syx, Sxy, and Sx as the blocks. And this is where we recall the formula for the determinant of a block matrix. So the determinant of Sn is equal to the product of the determinant of Sx and the determinant of Sy minus Syx times Sx inverse times Sxy. Here we can invert Sx because we assume the sample size is larger than the dimension of x, which is q. And so using this, we can rewrite our test statistic. And so we can see how lambda to the power 2 over n, when we write it as a ratio of generalized variances, we can cancel out the determinant of Sx, and we're left with the determinant of Sy minus Syx Sx inverse Sxy over the determinant of Sy. Now we can use the properties of determinants. So the determinant of an inverse matrix is the inverse of the determinant and vice versa. So we can bring the inverse of sy to the numerator. And next we can use the fact that the product of a determinant is equal to the determinant of the product of the matrices. And so we can bring in sy inverse inside the determinant. And this cancels out the first summand, and we keep track of the inverse of y on the right-hand side. We can again use the same property of the determinant if we multiply by the inverse of sy. If we multiply by sy to the 1/2 on the left-hand side, and on the right-hand side, and on the left-hand side we can multiply by sy to the negative 1/2. And this allows us to show that lambda to the power 2 over n can be written as the determinant of the identity matrix minus m hat transpose, where m hat transpose we defined when we talked about the sample canonical correlation analysis, which is simply the product here in the determinant. So why is this important? It's important because we know what the eigenvalues of m hat transpose are. The eigenvalues are the canonical correlation squared. And so putting all of this together, we've proven that lambda to the power 2 over n is equal to the product of 1 minus rho hat I squared, which is what we wanted to show. And so we see the connection here between a test for independence and canonical correlation analysis. So now that we have a test statistic, we need distribution under the null hypothesis to perform hypothesis testing. So for large n, we know that the statistic minus 2 log lambda is approximately chi squared, with degrees of freedom equal to p times q, which is the number of free parameters. And we can also use Bartlett's correction, which uses a different statistic. So we, instead of having minus 2, instead of having minus n log product of 1 minus rho hat I squared, we get this term here. So n minus 1 minus half of p plus q plus 1. But we keep the same null distribution. So for large n, this statistic with the Bartlett's correction is also approximately chi squared on p times q degrees of freedom. So let's look at an example of how to use this in practice. So we'll move away from the olive data set and use a different example this time, coming from the field of vegetation ecology. So we have two data sets. We have var e chem, which contains 14 chemical measurements from the soil, and var e spec, which contains 44 estimated cover values for lichen species. And the data has 24 observations. So n is larger than 14, but of course it's smaller than 44. So if you want more details about the data set, you can look at this 1995 paper by Faré, Otonen, and Oksanen. So the data is available in the vegan package. And next we import the data sets, var e spec and var e chem. As I mentioned, there was too many observations in var e spec. There was 44 variables, but we only have 24 observations. And so we'll pick the first 10, which correspond to, so the first one being cal v ulg, and the 10th one being diff comp. And so Y is going to be a matrix with 24 rows and 10 columns. Next, instead of using all the chemical measurements, we'll use the model that is suggested in the help page for the vegan package. And it's the following model. So we define it using a formula, and we can see there's 4 main terms, main effects, one coming from aluminum levels, one coming from phosphorus levels, one from potassium levels, and then bare soil. And we also have two interaction terms. So an interaction between phosphorus and potassium, and interaction between phosphorus and bare soil. So now X is a matrix with 24 rows, just like Y, and 6 columns. So we can do CCA on X and Y, and we can store the output in decomp. And next, we can compute the likelihood ratio test using the canonical correlations. And we get a value of 156 for the likelihood ratio test statistic. And next, if we compute P and Q, so P is the minimum of the dimensions of Y and X, and Q is the maximum of the two dimensions. And we use this to compute the critical value, and we test whether the likelihood ratio test is greater than the critical value. We get true. So we do reject the null hypothesis. Next, let's see what happens when we use the Bartlett correction. So again, the test statistic is a bit different. But the null distribution, or the approximation to the null distribution that we use, is the same. And so we can compare both test statistic to the same critical value. And so we see that on the one hand, we had 156 for the first test statistic. With the Bartlett correction, this goes down to 94. But when we compare with the with the critical value, we still reject the null hypothesis. So it's still greater than the critical value. So that was the first topic on large sample inference. The second topic is about sequential inference. And so the likelihood ratio test above was for independence. So when the covariance matrix is equal to 0 under a normal distribution, which of course implied that all of the canonical correlation at the population level were also 0. And so if we reject the null hypothesis that they're all equal, it's natural to ask how many are actually equal to 0 and how many are non-zero. And so we're going to do this sequentially, so testing one hypothesis after another. And so we can define a sequence of null hypotheses, H0k, where H0k is the null hypothesis that the first k canonical correlations are non-zero, but the remaining ones are equal to 0. And so you can see how you could start with a test of independence, and then if you reject it, you can move on to H01, which would be the null hypothesis that row 1 is non-zero, but the other canonical correlations are equal to 0. Then if you don't reject, you would stop there, and if you do reject, you would move on to H02, and etc., until you fail to reject a null hypothesis. And the way to do this, given the test statistics that we had, is to use a truncated version of the likelihood ratio test. And so instead of using the product of 1 minus rho hat I squared for I going from 1 to p, instead we're going from k plus 1 to p. And the null distribution for this likelihood ratio test statistic with the Bartlett's correction is approximately chi-squared on p minus k times q minus k degrees of freedom. So let's see how we can do this on the data set that we just analyzed. So we did reject the null hypothesis for independence. And so next we're going to check how many of these sequential null hypotheses we reject. And so the first line here computes the truncated likelihood ratio tests for all null hypotheses at the same time. And I'm doing this by taking the reverse of the canonical correlations. And so instead of having the canonical correlations ordered from 1 to p, they're ordered from p to 1, so in reverse order. And so when I take the cumulative product, the first cumulative product is going to be simply going to be 1 minus rho hat p squared. Then the second cumulative product is going to be 1 minus rho hat squared p times 1 minus rho hat squared p minus 1, and etc. And so we do this for all p values. We take the cumulative product, the log, and then we reverse again so that we start with h01 and then move on to h02. So the object log underscore CCS contains not the test statistic itself, but the test statistic modulo the constant that we compute on the second line here. So LRTs is going to be this constant coming from the Bartlett correction times the log CCS. And so we see that we get 6 test statistics here. So the first one is 94.4, the second one is 58, etc. And so we can compare all of these against their respective critical values to check which ones we reject and which ones we fail to reject. And so if I go to the next slide, and so I get, I use the fact that q chi squared is a vectorized function, so I can pass a vector of degrees of freedom. It's going to compute the critical values for all of the different values of the degrees of freedom. So I can compare LRTs against all of these critical values, and we see that we only reject the first null hypothesis. So recall that we started by rejecting the null hypothesis of independence, and so at least one of the canonical correlations is non-zero. And so we tested whether it was non-zero, and then we rejected, but we failed to reject the second null hypothesis. And so in other words, there's only one significant canonical correlation, the first one. We can maybe to clarify things a little bit, we can look at a graphical summary of what's going on. And so here on the x-axis, I have k, that's going from 0 to 5, and on the y-axis, it's the value of the test statistic and the critical values. So the blue line is the test statistic, LRT, and the red line is the critical value. So you can see that for k equals to 0, so the first test we did, the likelihood ratio test is greater than the critical value, but then the curve dips down below the curve for critical values, and we failed to reject all the subsequent null hypotheses. And so we only reject the first one. And so this is the last slide on large sample inference.